Hey guys, this video starts our study of electrochemistry, and in particular this video is about how to balance redox or oxidation-reduction reactions. And we're going to use something called the half reaction method. So it ends up that when we're balancing redox reactions, we have to calculate what are called oxidation states of all the atoms in the reaction. Oxidation states is just a kind of a bookkeeping method for electrons. It lets us see where electrons are going to and where they're coming from. Sometimes oxidation states end up being the same number as a formal charge or the charge, but not always. So it probably shouldn't, well, you shouldn't think of them as actual charges, just a bookkeeping method. So anyway, to calculate the oxidation number, oxidation state, same thing, for every atom in a reaction, we follow this list of rules, and this list is hierarchical. What that means is when two of these rules conflict, the one that's higher up, closer to the top, is one that we apply. It wins. So the first rule says that if we have an element in its elemental form, so like, hydrogen H2 or something like that, its oxidation state is 0. Next one we apply every time there is more than two elements in a compound. This says that when we add up the oxidation numbers for all the atoms in that compound, they must be equal to the overall charge. And if there's no charge, then that's 0. And next we have rules for the oxidation states of specific elements. So fluorine's at the top of the list. Its oxidation state is -1. Next, 1A metals, so potassium, sodium, and so on, are +1, and 2A metals, so magnesium, calcium, strontium, and those are +2. Hydrogen's +1, oxygen's -2. Now the halogens, the 7A elements, are -1. Now notice what I say here is except fluorine. That's because fluorine is already up here, and this rule up here for fluorine beats these elements here. It's applied if they conflict. But any other halogen, is lower than these, so the higher up elements rule is what is applied. And then finally, nitrogen is -3. So let's practice. Calculate the oxidation numbers or oxidation states for each atom in these compounds. Xenon trioxide difluoride, iron 2,3 oxide, also called magnetite, and acetylene. So guys, why don't you work that out real quick and come back when you get your answers. Welcome back, guys. So for xenon trifluoride dioxide, we have rules for oxygen and fluorine, but not xenon. When that's the case, we apply the rules for the elements we have rules for and solve for the one we don't. So there's one xenon, so whatever its oxidation state is, plus 3 oxygens, they're -2, plus 2 fluorines, they're -1. When we solve this for the oxidation state of xenon, we see that it's +8. There we go. In magnetite, iron 2,3 oxide, we have a rule for oxygen but not for iron, so we apply the rule for oxygen, solve for iron. So there's 3 irons, 4 oxygens, each is -2, the oxidation states. When we solve this, we see that the oxidation state for iron is +8/3. So a couple things about this, guys. First, when we solve for oxidation states, they don't always have to be integers, but what's going on here, okay, is we can't have a fraction of an electron, right? So what's going on here is in this substance here, it's called iron 2,3 oxide or magnetite. This substance is actually a mixture of iron 2 oxide and iron 3 oxide, FeO and Fe2O3. And it ends up the average oxidation state for iron in that mixture is +8/3. So between 2 and 3. Next, acetylene. So we have a rule for hydrogen, but not for carbons. So 2 carbons, 2 times hydrogens plus 1. We see that carbon's oxidation state is -1. All right, there we go. Next, oxidation and reduction. So this is a little mnemonic that helps to remember what oxidation and reduction are. So oil rate. Oil stands for oxidation is loss of electrons. And so if anything, whatever is losing electrons as we go from the left to the right of the arrow is being oxidized. And the way we can tell that, this is what oxidation states are for. if the oxidation state of some element becomes more positive or less negative as we go from left to right, that's what's being oxidized. Likewise, reduction is gain, rig, of electrons. So if something gains electrons, it's being reduced, and we can tell that by calculating the oxidation state on both sides of the arrow. If the oxidation state becomes less positive or more negative, that thing is gaining electrons, it's being reduced. Now, if it wasn't confusing enough already, we have agents. So whatever is being oxidized we call the reducing agent. And the reason for this is that when a species is oxidized, it loses electrons. Well, those electrons have to go somewhere, and wherever they're going to, that species is being reduced. So the thing that was being oxidized is the agent by which the other thing is being reduced. So we call it the reducing agent. Likewise, whatever is being reduced is the means by which something else is being oxidized. It's taking the electrons from somebody else, so it's called the oxidizing agent. Now, the way we can tell if a chemical reaction is a redox reaction, is if the oxidation states change as we go from the left to the right of the arrow. Not all chemical reactions are redox reactions, but this is how we can tell. So, some examples here. First of all, are these redox reactions? So are oxidation states changing? Second, if so, what's the oxidizing agent in each of these and what's the reducing agent? So these are two separate reactions. So we're going to do that, all this to this first one and then to this one. So why don't you guys work that out real quick and come on back when you get your answers. Welcome back, guys. So first one, decomposition of potassium chlorate. Now here, we have rules in the rules for calculating oxidation states for all the elements here, potassium, chlorine, and oxygen. So what we do is whatever is lowest in that list, so chlorine is a 7A element, it's a halogen, that's of these three elements, its rule is lower down than everything else. So we do not apply that rule, but rather we solve for this. But we apply the rule for the other elements. So potassium is a 1A metal, and oxygen is oxygen. So when we apply those rules, we see that the oxidation state for chlorine here is +1. On the other side, in potassium chloride, we can just apply the rules and we get the right answer, or we can solve for chlorine, we still get -1. So we see now that chlorine is going from a +1 oxidation state on the left-hand side to a -1 on the right. It's becoming less positive or more negative. It's being reduced. Now oxygen goes from -2 here, and here on the right-hand side, we're applying the very first rule that says that an element in its elemental form has an oxidation state of 0. This is the elemental form of oxygen. Its oxidation state is 0. So oxygen goes from -2 to 0. It's becoming more positive or less negative. It's being oxidized. That means that chlorine is the oxidizing agent because it's being reduced, and oxygen is the reducing agent because it's being oxidized. Now over here in the second reaction, we get these oxidation states, and you guys should make sure you're getting the same numbers. And now look at this. So first, hydrogen is +1 on both sides, it doesn't change. Oxygen's -2 everywhere on both sides, it doesn't change. The only species that's changing the oxidation state is nitrogen. It goes from +4 in nitrogen dioxide to +2 in nitrogen monoxide, but +4 in nitrogen dioxide to +5 in nitric acid. So that means that nitrogen is being both oxidized and reduced. It's being reduced when it goes from +4 to +2. It's being oxidized when it goes from +4 to +5. So nitrogen's both the oxidizing agent and the reducing agent here. Now physically, guys, what's happening here is some of the molecules of nitrogen dioxide end up as nitrogen monoxide. In those molecules, the nitrogen is being reduced. And some different molecules of nitrogen dioxide end up as nitric acid. In those molecules, the nitrogen atoms are being oxidized. And there we go. Now, how to balance redox reactions. So this is a list of steps that you follow. This right here, this is how you do it. Couple of things. First is redox reactions will happen in either acidic solutions or basic solutions. And the way you know that is sometimes you're just told in the problem this occurs in acidic solution or basic solution. Sometimes you can tell by looking at the reactants whether or not it's going to be acidic or basic. I mean, if one of the reactants is an acid, then it has to be in an acidic solution. If it's acidic, we do steps 1 through 7 and stop. If it's in a basic solution, we do steps 1 through 7 and then continue on and do steps 8 and 9. So let's practice. So we want to balance this equation using the half reaction method. We're told that it occurs in acidic solution. Now, a couple things. This is a net ionic equation, and I recommend always starting with a net ionic equation when you're doing balancing redox reactions. It's so much easier and less messy. But you're not always given net ionic equations. Like, this is a complete equation, right? This has the counter ions in it. If you get something like this, then, I mean, you can balance this. It's a little bit messier, but it still works out. But what I usually do is I cancel out any spectator ions, which in this case would be potassium. There's no sodium over here, but it would be up here. Chlorine, right? That's a spectator ion. And then balance it from there. So I'd start with this. The other thing, though, about being given this complete equation is that we see an acid, hydrochloric acid here. So if we're, here we're told it's acidic solution, but if we're told whether or not it's acidic or basic, but we see the acid over here, we know it's acidic. All right, so the first thing is, step 1 is to write out what are called the half reactions. So let's do that. The oxidation and reduction half reactions. So what that means is, first thing you do is you calculate the oxidation states for every atom in this reaction. And we see that chromium on the left goes from a +6 to a +3 on the right. So that's reduction. The reduction half reaction will be those species. Dichromate on the left, chromium 3 on the right. We see that the carbon in the oxalate anion goes is a +3 oxidation state, whereas on the right-hand side, the carbon is +4 in carbon dioxide. So it's becoming more positive, less negative. That's oxidation. So these things are what are involved in the oxidation half reaction. Oxalate on the left, carbon dioxide on the right. Now, these aren't balanced yet, but that's what we're doing, is we're balancing them. That's step 1. Step 2 says balance everything except oxygen and hydrogen. So, and then before we do, I put this yellow 2 here to balance it, but before I did that, we had 2 carbons on the left, 1 on the right, so I put a 2 here as a coefficient. That's how you balance them, with the coefficients, right? And now we have 2 carbons on both sides. We're leaving the oxygen and hydrogen alone. Next, down here in the reduction half reaction, we have 2 chromiums on the left. We only had 1 on the right, so once more I put a 2 as a coefficient here. Now we have the chromium atoms balanced. Everything except oxygen and hydrogen are balanced. Now we go into the oxygen and then the hydrogen. So step 3. Balance the half reactions for oxygen by adding waters for every oxygen you need. So to balance the oxygens, because there's 1 oxygen in water, you add however many waters that you need to balance out the oxygens. So in the oxidation half reaction, once we put this 2 here to balance the carbons, that gives us 4 oxygens on the right. We already had 4 on the left, so they're already balanced. We don't have to do anything. But when we come down here to the reduction half reaction, we have 7 oxygens on the left, and we didn't have any on the right, so we needed 7 more oxygens. So I added 7 waters. It gives us 7 oxygens. We'll get to the hydrogens in a minute. But now, we've balanced the oxygens. We'll move it on to step 4. It says balance the hydrogens by adding the hydrogen ion, H+, for every hydrogen atom that you need. Well, there's none in the oxidation half reaction, so we're done, that one. For the reduction half reaction, though, before I do this, we had 7 times 2 is 14 hydrogens on the right and none on the left. So we needed 14 hydrogens on the left. So I added 14 hydrogen ions, 14 H pluses. And now hydrogens are balanced. Step 5. This one, balance the charge in both half reactions with electrons. So be extra careful on this step, guys, because my experience is that if somebody makes a misstep when they're balancing redox reactions with this method, this is a step that they get off on, that they miss. So remember, each electron has a -1 charge, and that's the only tool we have to balance charge. So before I do that, we see that in the oxidation half reaction, there's 2 negative charges here, 0 over here, so I need 2 more negative charges on the right, so I add 2 electrons. Now the charge is balanced. Now in the reduction half reaction, before I add the electrons, we have 2 times 3 is +6 on the right, On the left, we have 14 positives minus 2 is 12 positives. So we need 6 negatives on the left to cancel out 6 of those positives, so they end up with 6 positives also. So we add 6 electrons. Now, at this point here, you should always take a second and do a little check. Oxidation is loss of electrons. That means that once you guys have gone through this process, the electrons in the oxidation half reaction better be on the right-hand side, because that's how we show that they're being lost. If somehow in your oxidation half reaction you ended up with electrons on the left, something went wrong, and I'd recommend just starting back at the beginning. Likewise, because reduction is gain of electrons, the electrons in the reduction half reaction have to appear on the left. Again, if they don't, then just kind of start over. Don't try to fix that. All right, so there we go. Now, step number 6. Make the number of electrons the same in both half reactions by multiplying by some integer. If necessary, sometimes you don't have to. So in the oxidation half reaction, we had 2 electrons. In the reduction half reaction, we had 6. Well, basically what we're doing, guys, is we're looking for the least common multiple of these two numbers. In this case, it's 6. So we leave the reduction half reaction alone, and we multiply the oxidation half reaction by 3. Every coefficient gets multiplied by 3. So we end up with 3 oxalates, 6 carbon dioxide, 6 electrons. The point of this is to ensure that we have the same number of electrons in both half reactions, so that they cancel in the next step. Moving on to step 7. Add up the 2 half reactions to get the overall balanced equation. And so remember, when we add reactions, chemical reactions, if something appears on the left side of one equation and on the right of the other, they cancel. So we set this up to make sure the electrons cancel, and they do. That, in this case, that's the only thing that cancels, so everything that's left is our overall balanced equation. So 3 oxalates, 4 hydrogens, plus dichromate, going to 2 chromium 3s, 7 waters, and 6 carbon dioxides. Now, this is a balanced equation, redox reaction. You should always check yourself. It's real quick. And here we have to check 2 things. Not only must the mass be balanced, but the charge must also be balanced. So checking the mass balance is what we're used to. We say there's 3 times 2 is 6 carbons on the left, 6 times 1 is 6 carbons on the right. Carbon's good. Oxygens, 3 times 4 is 12, plus 7 is 19 oxygens on the left. 7 times 1 is 7, 6 times 2 is 12, 7 plus 12 is 19 oxygens on the right. Oxygens balanced. 14 hydrogens on the left, 7 times 2 is 14 on the right. 2 chromiums on the left, 2 chromiums on the right. We already did oxygens. All right, the mass is balanced. Now the charge. On the left, we have 3 times negative 2 is negative 6, plus negative 2 is negative 8, and then 14 times 1 is positive 14. So positive 14 minus 8 is positive 6 on the left. On the right, we have positive 6. 2 times 3 is positive 6. There we go. By the way, when we get to this point, right before we cancel the electrons, the number of electrons that we have in both half reactions that we made the same, that's how many electrons are being transferred in this reaction. That's a useful thing to know. We're going to see that later in this material. So now we're going to balance another redox reaction using the half reaction method. This one occurs in basic solution. That's what we're told. Now that's the net ionic equation. The complete equation might look something like this: potassium cyanide, potassium permanganate, potassium cyanate, and manganese 4 oxide. You can tell that this is going to be basic solution because this is the salt. Potassium cyanide is a salt of the conjugate base of a weak acid. So hydrocyanic acid is a weak acid, which means that its conjugate base, the cyanide ion, is a base. It's going to be a basic solution. So let's begin. Actually, you know what? Be good for you guys to give this a shot yourself. So do just what we did. Now we're going to have to do steps 8 and 9, which are pretty easy, but at least get through step 7, and then come on back when you get your answer. Welcome back, guys. So writing the half reactions, we see that carbon in cyanide goes from a +2 oxidation state to +4 in cyanate, and that means it's being oxidized. So these 2 species are in our oxidation half reaction, cyanide going to cyanate, and manganese in permanganate goes from a +7 there to a +4 in the manganese 4 oxide. So it's being reduced, less positive, more negative. And so the reduction half reaction has these two things in it: permanganate, manganese 4 oxide. That's step 1. Going to step 2. Balance everything except oxygen and hydrogen. Well, this is easy for this one because it's already done. 1 carbon, 1 carbon, 1 nitrogen, 1 nitrogen, 1 manganese, 1 manganese. There we go. Let's move on to step 3. Balance oxygens with waters. So the cyanate side of the oxidation half reaction has 1 oxygen, none on the left, so we add 1 water. Here in that reduction half reaction, we start out with 4 oxygens on the left, 2 on the right. We need 2 more oxygens, so we add 2 waters. Moving on to step 4, balance the hydrogens. So here we have 2 hydrogens on the left, none on the right, so we add 2 H pluses. Here we had 2 times 2 is 4 hydrogens on the right, none on the left, so we add 4 hydrogen ions. There we go. And step 5, balancing the charge with electrons. So at this point we have a -1 charge on the left. We have -1 plus +2 is +1 on the right. That means we add 2 electrons, and that gives us a -1 charge on both sides. And yes, the electrons did appear on the right-hand side of the oxidation half reaction. Down here, we had 0 charge on the right. We had +4 minus 1 is +3 on the left, so we add 3 electrons to get to 0. And yep, the electrons appeared on the left-hand side in the reduction half reaction. Moving on to step 6, getting the electrons the same number of electrons. Well, the least common multiple of 2 and 3 is 6, so that means we're going to multiply through the oxidation half reaction by 3 to get 6 electrons, and the reduction half reaction by 2 to get 6 electrons. And when we do, we end up with these equations down here. Now we're moving on to step 7. Add them up and cancel out. So in this case now, of course the electrons cancel, but we also, in the oxidation half reaction, we had 3 waters on the left. In the reduction half reaction, we had 4 waters on the right. 3 of these waters cancel 3 of these, leaving 1 on the right in the reduction half reaction and none in the oxidation half reaction. Likewise, the hydrogen ion, we had 8 hydrogens on the left of the reduction half reaction, 6 on the right of the oxidation half reaction. These 6 hydrogen ions cancel 6 of these, leaving 2 behind. There's none now in the oxidation half reaction. When we add this up, we get the overall balanced equation. 3 cyanides, 2 hydrogen ions, 2 permanganates, 3 cyanates, 2 manganese 4 oxides, and water. Now, we're not done now because we still have to do steps 8 and 9, add the hydroxides and cancel waters. So let's see what that looks like. So this is actually steps 8 and 9 combined. So we're going to add, for every hydrogen ion we have in this balanced equation, we add 1 hydroxide to both sides of the arrow. So because we ended up with 2 hydrogen ions on the left, we add 2 hydroxide ions to both sides. Now, the side that had the hydrogen ions in it, the hydroxide plus hydrogen ion always makes H2O, right? Water. So these are converted into water molecules. So we have 2 waters on the left, and then the hydroxides stay over here. Now in this case, we had 1 water on the right, and so this is really step 9. We're canceling out the water. So this 1 water cancels 1 of these, and we have 1 water that's left behind. So then we write that down, and that's our balanced overall equation. But we still have to check mass and charge balance. So let's do that real quick. So we have 3 carbons on the left, 3 carbons on the right, 3 nitrogens on the left end, 3 nitrogens on the right. 2 hydrogens on the left, 2 times 1 is 2 hydrogens on the right. 1 plus 2 times 4 is 8 is 9 oxygens on the left. 3 times 1 is 3, 2 times 2 is 4, 4 and 3 is 7, plus 2 more is 9 oxygens on the right. Oxygens are balanced. And then finally 2 manganese on the left, 2 manganese on the right. All right guys, mass is balanced. Let's check the charge. We have 3 times 1 is -3, 2 times 1 is -2. We have -5 overall on the left. We have 3 times 1 is -3, 2 times 1 is -2, -5 on the right. There we go. Balanced with both mass and charge, and we're finished. And that's all there is to that, guys.